Okay. So the problem that I gave you for Monday is in Wednesday's folder. The formal problem is at the end of the PowerPoint presentation. So I put a note in the folder that says that's where the graded practice problems for Monday is. I'll have your exams back to you on Monday. I won't release the key until that point, and the grades won't be released until after classes. Okay, we are up to Chapter 10, E2. Does anybody have any questions to start with on E2?
Can we talk about how to get the molecule in the anti-Periplanar configuration for the side?
Yes. So in an E2 mechanism, we're going to use a base. We're going to use a strong base in order to make the reaction go. And in this case, the base is going to take an active role in grabbing the beta hydrogen and starting the process. When we did E1, just sort of as a comparison, when we did E1 and we formed the carbocation and we lost the H+, sometimes the book or you'll see the mechanism where there's something like a water that comes in and grabs the hydrogen and then the H+ gets pulled off by that water and the double bond forms. I don't normally show anything coming in and getting the hydrogen because I don't want to leave the impression that this is actually what's causing the reaction to occur. In this case, it's kind of like the H+ is going to leave and it's got to bond to something. And so the water's there to catch it. The water's not reaching out and ripping the hydrogen away. It's just kind of like catching it as it falls away. So if you show that, that's fine, and the book will oftentimes show this. But in an E2 reaction, we're going to use a base to start the process and rip that hydrogen off. So the base is taking a much more active role. And in an E1 versus an E2, the stereochemistry is such that you have to have your beta hydrogen and your leaving group, and I'll just make this a generic leaving group. The beta hydrogen and the leaving group must be in an anti-periplanar geometry. And what that means is, that means they're anti and they're in the same plane. I think there's another term for this that books use. I don't use it. I just call it anti-periplanar because that fits with what we talked about before. So in other words, if I'm looking down this bond, what I'm seeing is I'm seeing the leaving group here and the beta hydrogen that will be removed in the anti-position. Now there is such thing as periplanar, which would be the hydrogen and the leaving group are in the same plane, kind of eclipsed. But the geometry has to be that the beta hydrogen and the leaving group have to be anti-periplanar. And then the base will come in, whatever that base is, which we'll talk about. The base comes in, grabs the hydrogen, the pair of electrons goes to form the double bond, and the leaving group all leaves at the same time. Over here, that means the base would come in, grab this hydrogen, have that pair of electrons move, and then have the leaving group leave. So they have to be anti-periplanar because of the way the orbitals will overlap as you go through the transition state. So just so that you know, the transition state for this reaction would look like this. you would have whatever your base is with a delta minus charge bonded to the hydrogen. Then the hydrogen's going to be breaking its bond, so it's going to be on a dotted line. Then you're going to have a dotted line of forming the double bond, and then a dotted line to the leaving group. And then we would have the rest of the molecule. The leaving group's going to leave as a delta minus, or leave as a minus, so it's going to be delta minus as well. So this would be a standard transition state for any of the E2 reactions. Partial bond between base and hydrogen, hydrogen-carbon bond breaking, carbon-carbon double bond forming, carbon leaving group breaking. And so the dotted lines would look like that. And the only real charges would be the base at delta minus and the leaving group at delta minus as well. So that would be a standard transition state for that reaction. I haven't answered your question yet, but I'm getting to it, just so we're all on the same place. Okay. Is everybody okay with that? Did I need to do that? I did it anyway. So now let me just backfill this in terms of, so why didn't we worry about any kind of anti-periplanar transition state for E1? And the reason that we didn't do that for E1 is because if you think about the carbocation, it's got its empty p orbital that gives it the positive charge. All that has to happen there is the beta hydrogen just must be planar to one of the p orbitals that's empty. It still had to be periplanar, I guess, to that, but it didn't have to be anti, because the hydrogen could be planar to that empty orbital, or down here it could have been planar to that empty orbital. It just has to be planar to that. So in this case, there wasn't a restriction on whether there's going to be a restriction in rings that the beta hydrogen must be trans to the leaving group, but there will not be that restriction when it comes to E1 reactions, because the hydrogen could be cis to the leaving group or trans to the leaving group, because after the leaving group leaves, there's nothing to be cis or trans to. It just has to line up with one of those two orbitals. So it's really, the hydrogen does have to be periplanar, but it doesn't have to be anti-periplanar. But in E2, it has to be anti-periplanar. And I'll just add one more thing for completeness. The reason that the hydrogen has to be anti-periplanar is because if I write out the orbital picture of this, the orbital picture would look like this. Here is my hydrogen attached to the carbon, and here is my, I'll just make it an X leaving group attached there. So what happens is that when we go to the transition state, those two orbitals, let's see, they're oriented this way. Those two orbitals are going to have to slide up and become parallel to overlap then to form the double bond. So what will happen is as the hydrogen gets pulled off and the leaving group leaves, those orbitals will not only slide up and become p orbitals, and one p orbital will have a pair of electrons and the other p orbital will be empty, so that then they can overlap to form the double bond. But as they slide up and become parallel, the little tiny sp3 hybrid orbitals that we've invoked here in SN2, what's going to happen is that electron density is going to start filling in. So not only do they slide, but they become more equal in those two lobes, so that when they get to the transition state, they're almost full p orbitals. And So the transition state's going to look something more like this. And then they'll go ahead and overlap to form the double bond. So in order to be the most efficient to get to the transition state, you have to have those two orbitals parallel to each other. And you have to have the hydrogen with its big lobe moving or being lost this way so that the electron density can feed down into this. And then you have to have the little electron density down here so that basically that can become empty in order for it to overlap. So this has to be anti-periplanar from the standpoint of this pair of electrons then overlapping over here. If the hydrogen isn't anti-periplanar, then what would have to happen is you'd have to bring the hydrogen to be anti-periplanar and then have the reaction to occur. So this gives you the smoothest and lowest energy traveling to the transition state. So that's the reason why it has to be anti-periplanar, is because then the orbitals move in one efficient way to get to the transition state, which is going to give you a lower energy. The more movements of atoms you have to make, the more energy it takes, and the higher the transition state energy. So this way, it's the smoothest way to get there. And so that's why it has to be anti-periplanar. Over here, since the sp3 hybrid orbital just has to line up, you still have to have a periplanar, but it doesn't matter whether the hydrogen is overlapping the top empty orbital or the bottom. So you could have two possible orientations here. The hydrogen could be up or the hydrogen could be down. Okay. So that's why the reaction has to be anti-periplanar. Okay. Everybody with me? So then the question is, what are the consequences of that? And the consequences of that are that if I give you a molecule that has bold and dashed wedges, we have to somehow rotate around the carbon-carbon bond to put the beta hydrogen anti-periplanar to the leaving group to get the correct stereochemistry of the alkene. So here would be an example. And there are some of these problems in Top Hat. I know I wrote an explanation to at least one of these last night on Piazza. So let's say I've got a hydrogen, I've got a methyl group, and I've got an ethyl group here. And then over here I've got a chlorine, a hydrogen, and another methyl group. And I'm going to do an E2 reaction. I'm not going to specify the base right at the moment, but that will play a role. So if I do this E2 reaction, you're going to get two products. Okay? We're going to get two products out of this reaction. And those two products are going to come from the loss of a beta hydrogen and the chlorine leaving group. So the way we go about this is we say, okay, we go back to basics here. With E1, what did we have to do? In order to write the product, we needed to identify the alpha carbon and the beta carbon and the beta hydrogens. Now, the alpha carbon had the leaving group. It became the carbocation. If there's a rearrangement, you have to reorient the alpha carbon. But we need to know what are the alpha and the beta carbons and hydrogens. So in this case, this is my alpha carbon. I have 1, 2 beta carbons. And each of those has a hydrogen, so therefore I'm going to get a product. Except that now in the E2 reaction, I have to make sure that the beta hydrogen can become anti-periplanar to the chlorine, because if it doesn't, there's no reaction. Okay. So the easiest product for us to get is to get it off, is to form the double bond to this beta carbon. And for that beta carbon, if I rewrite the structure down here, well, let's rewrite the structure like this. Let's take and rotate the right carbon, and I need to put the chlorine down here on this regular in-plane bond. And then I'm going to have to put this beta hydrogen over here on this one in order to get the proper stereochemistry. But let's just rotate that down. So if I rotate the chlorine down into the methyl group, the chlorine goes here. The methyl group goes up to where the hydrogen was, and the hydrogen comes down here. And let me rewrite this as a CH2H. So here's my alpha carbon, here is my beta carbon, here is my beta hydrogen. Okay. Now, just looking at that arrangement, the beta hydrogen has to be anti-periplanar to the chlorine. When you have a CH3 group, any of those three hydrogens could be anti-periplanar, and I could rotate any of those three hydrogens to be anti-periplanar. So in this case, this is easily, the base is going to come in, it's going to grab that hydrogen, that pair of electrons is going to go here, and the chlorine is going to be kicked off. And so the first product would have the double bond to the CH2 group, and then the other bond would be to the hydrogen. And then over on the left-hand side, nothing changes. So there's an ethyl group there if I want to abbreviate a hydrogen, and then a methyl group. So product number A is going to be that product. So the first step is going to be determine your alpha and beta carbons and beta hydrogens. The second step is to make sure that the beta hydrogen can become anti-periplanar to the leaving group. And then the third step is going to be then to have the base remove that beta hydrogen in its anti-periplanar geometry to give you the product. And then we'll talk about major products here in a minute. Okay. So this would be product number one. And all three of those hydrogens could be anti-periplanar, so there's really nothing, there's no stereochemistry to really mess with here. The CH3 is going to become deprotonated. I'm going to form the double bond. Does that make sense? So I didn't even have to put it in bold and dashed wedges because CH3, any of those three is going to be removed. But now if I want to deprotonate the left-hand beta hydrogen, I have to put it into the anti-periplanar geometry to write that product. So if I rotated my right carbon here so that I have my CH3 group, so I'm going to write another deprotonation so that CH3 is intact. I have my hydrogen here, and then I have my chlorine here. I now have to take my left carbon, and I've got to rotate it so that this beta hydrogen, that beta hydrogen is going to be up here so that it can be anti-periplanar to now my leaving group. So if I rotate this hydrogen up into the position in the plane, then the ethyl group will come down here, and then the methyl group will go back where the hydrogen is. Now I have this beta hydrogen in a position where it's anti-periplanar to the chlorine. And now the base can come in and grab it. But because of the fact that the groups are on bold and dashed wedges, I'm only going to get one stereochemistry of the double bond. Okay. The double bond is not going to be a mixture of where the methyl groups may be cis or the methyl groups may be trans. It's going to be one or the other. And that's going to be my major product. So we manipulated these kind of sawhorse projections if we had to rotate and do R&S on them, or better yet, we manipulated these sawhorses not as sawhorses, but as Newman projections when we were writing all the conformations. So this is the same kind of procedure, except with the sawhorse. And you could do this with a Newman projection if you wanted to. The whole purpose is get the hydrogen and the chlorine anti in the Newman projection. So once I have it like this, then my base comes in, grabs the hydrogen, this pair of electrons moves here, and the chlorine gets kicked off. Now the critical part of this is that when you're writing the carbon-carbon double bond, the groups that are bold are going to be cis, and the groups that are trans are going to be, the groups that are bold are going to be cis. The groups that are dashed are going to be cis. So over here, I have a methyl and an ethyl group. And it wouldn't matter whether I put the methyl group or the ethyl group on top or bottom. What's critical is what two groups over here, what group is cis to the methyl, what group is cis to the ethyl group. And so in this case, the ethyl group and the methyl group are both on bold wedges. They become cis. The methyl and the hydrogen are on dashed wedges. They now become cis. So that this is the stereochemistry of that alkene product, not the other. Because the other can't be formed because the beta hydrogen, when it's anti-periplanar to the leaving group, only gives this stereochemistry. So this is product B. So that's the critical part, is that the bold have to be cis and the dashed have to be cis. And you have to manipulate the molecule in order to get the beta hydrogen, in this case on the left, that beta hydrogen anti-periplanar to the chlorine. And to start with, we'll say they should probably be both on the plane, the bonds that are in the plane of the screen or paper. So that's how we have to manipulate to get the proper stereochemistry in a non-cyclic system. Okay, so these would be my two major products, or these would be my two products of the reaction. Now, which one would be major is another question. But these would be my two possible products. Okay. All right. Does that kind of make sense? So I think problem, I did 10-10, 10-12, and 10-13 last night. And I put that on there as a note on Piazza, so that, well, you can download and print it or download it if you need to. But that's how we get that stereochemistry. So they ask some of those questions, I'll ask some of those questions as well. All right, so for a non-cyclic system, you basically have to find the beta hydrogens. If the beta hydrogen is on a boulder dashed wedge, then you have to adjust it or make the conformation where it is anti-periplanar that means you're only going to get one of the two possible double bonds. Okay. Everybody okay with that? I should probably test that. So let me test it. Okay, so let's say we started with this molecule, and I want to do an E2 reaction. This is actually going to be messier in terms of what are all the possible products, but I'm going to ignore that for the moment, and I'm going to say if the base comes in and grabs that beta hydrogen, what is the stereochemistry of the alkene going to look like? And it's a very simple question. Are the two methyl groups going to be cis, or are they going to be trans in the final product? So I'll give you a couple minutes, and then we'll see what that looks like. So I'm only concerned with the removal of that beta hydrogen in the square. So you need to put it in the right conformation and then write the product. Question is whether or not there's other relationships up there that are but that's the easiest one to see. Still make two other products. Yes. I don't know. Well, I just wrote the products. I didn't figure out the answer yet. I figured well, he's still like everybody's right.
then we're back to yeah, they don't have to be there, so that's one. Yeah. Yeah, I had
So yeah, you have to, it's easier to see in this case, they're in the same. Okay, so let's vote. Since it seems like most people have this. What are my two possible products? My two possible products are going to be to have the CH3 C double bond with the two CH3 cis and the two ethyl group cis as well. So we'll call that A. Having the methyl groups and the ethyl groups trans, we'll call product B. So let's vote on which one of these two you got. Did you get A or did you get B? Okay, so did you get A or did you get B? All right. Everybody got an answer? All right, we have 15 to 6 to 1. I don't know what the 1C is. But we've got 15 to 6. 15 to 6, B15, A6. Okay. So we have to put this into an anti-periplanar geometry with that hydrogen and with the chlorine. Now, the easiest anti-periplanar geometry to see would be to put the chlorine here and put the hydrogen here. There are other anti-periplanar relationships beyond just the one in the plane. For instance, the dashed bold would be anti-periplanar over here. And the bold and dashed would be another anti-periplanar. And then your bonds that have the same type of bond would become cis. So you don't necessarily have to put the hydrogen and the chlorine in the plane, but it's just easier to start that way to see it. But you can't have bold, bold, and you can't have dash, dashed, because that would be periplanar. Actually, it wouldn't be periplanar. It would be on the same. It would be peri, but no planar. So you have to make it anti-periplanar. So in this case, what would happen if I move the hydrogen up here, the methyl group comes to here, and the ethyl group goes there, if I want to abbreviate it. When I bring my chlorine down here, that means my ethyl group goes here, and my methyl group goes there. Now when I lose my hydrogen and chlorine, how did the double bonds go? Bold is ethyl and methyl, and dashed is methyl and ethyl. So it appears as though, wait, I completely messed that up, didn't I? Ethyl, methyl, bold, methyl, ethyl, dashed, and so they are going to be trans, which is the majority answer. Okay. So there is how we can manipulate this. Again, initially it might be best to just put the hydrogen and chlorine on the regular bonds, the bonds that are in the plane, and then the bold and dashed all become cis. Okay. All right, is that okay? Does anybody have any questions? So that's one of the problems that they're asking in Top Hat, as well as those are problems that I could ask you next week. We'll probably do problems on Monday that kind of wrap everything up, because the chapter 11 is we'll mop up whatever we have left in chapter 10, but chapter 11 is combining everything together, which we kind of have done as we've gone along here. Okay. Let's go back to this problem with our A and our B. Now in this case we only had one. We had two sets of beta hydrogens. But now the issue becomes, which one of these two is the major product, A or B? And the answer to that question is, it depends, which isn't an answer, right? But it depends on what? Well, it's going to depend on the base that I use. So I need to use a base. I can actually use a base to pick and choose between these two products. And what I'm going to do is I'm going to take advantage of steric hindrance. And so if I'm looking at this molecule where I have, let's say, the beta hydrogen here, the chlorine there, and then up here I had a CH2 with the other beta hydrogen. Then I have a hydrogen that is not a beta hydrogen. And then over here I have my ethyl and let's say my methyl group. The choice is between deprotonating that hydrogen and deprotonating that hydrogen. Now what's the difference between those hydrogens? This hydrogen is what kind of beta hydrogen? Primary, secondary, or tertiary? What kind of hydrogen is this one? Primary, secondary, or tertiary? What? It's primary. And then what kind of hydrogen is this one? Primary, secondary, or tertiary? Tertiary? We agree? We agree on those classifications? Because that's correct. The one on the left is tertiary, the one on the right is primary. So I can actually pick and choose which hydrogen I want to deprotonate based on steric hindrance. So my next question is, which one of those two hydrogens is more sterically hindered? Or has more steric hindrance around it? The primary or the tertiary? Which one has more steric hindrance around it? We agree? So tertiary has more steric hindrance around it. The primary one has less steric hindrance. So if I want to be able to pick between the tertiary and the primary, here's what I need to do. I need to choose my bases. Now, your book likes to use methoxide and ethoxide as examples of strong bases that you need, because E2 needs a strong base. And they classify these, and just so you're like, I've never seen a CH3 CH2O minus. Well, you have. They just put a sodium on it, right, as the counter ion. The counter ion doesn't particularly matter. Well, it does, but not in this. In this case, we're going to ignore the counter ions. And I usually don't like to put counter ions in because then they end up everywhere. They end up inside of cyclohexane rings, which I don't get, but they just end up showing up everywhere. Remember, these are spectator ions, so they don't even have to be there, but they do. Because if I want some methoxide, I need to go down to the stockroom and I have a choice. Do I want potassium methoxide? Do I want sodium methoxide? So, and they also will use this in the alcohol, so you'll see it as a sodium methoxide in methanol or sodium ethoxide in ethanol, because that's the classic way to make these. The classic way to make these is to take some methanol, carefully drop a chunk of sodium metal into it. The sodium metal reacts with the methanol like it does with water, forms hydrogen gas, and then it forms the anion. So this is what you see as those combinations. This is what we need to focus on. I will put in this classification, you'll see in my problems, an NH2 minus. And the reason NH2 minus is there is because, number one, it's a strong base because it's N minus. Remember that as we go across the periodic table from F to O to C to N, as we go this way, the basicity increases so that an N minus is pretty strong base. Now, there is an issue here that we'll come back to, that all strong bases are also strong nucleophiles. So the reason why I like to use NH2 minus is because NH2 minus, for some reason that's beyond the scope of this course, doesn't act as a nucleophile. So it's strictly a base. We're going to treat methoxide and ethoxide in this chapter as if they are bases. They are not strong nucleophiles, but they are. So we're going to ignore their nucleophile strength and just say, hey, you're a base for now. All three of these characteristics is that these are small bases. They are not sterically hindered, they are small. And so small bases have the ability to grab a primary or a tertiary because they're small. Now, I hate to do this, but chemistry is all about energy. That's the reason it occurs. So in this case, what happens is, if you use a small base, the transition state energies of the small base removing the hydrogen that's primary or tertiary, those transition state energies are going to be pretty close together. There's not going to be much difference because it's a small base. And so the mechanism isn't going to favor the lower energy transition states. And what that means is that these small bases can grab either one of the two hydrogens. What dictates the major product? The major product is dictated by the alkene and which alkene is more stable. That's what's going to dictate the major product. So if the small base can get to the primary and tertiary equally well, the major product is going to be the product that is most stable, which means that it's going to be the product that is most, it's an alkene product, the alkene product that is most substituted. Okay? So if you use these bases you're going to get the most substituted alkene is going to be the major product. There's one caveat, one huge caveat. The hydrogen that's being removed must be anti-periplanar, or must be able to become anti-periplanar to the leaving group. That has to happen. So, in terms of writing the major products, our steps are going to be identify the beta hydrogens, and then identify the beta hydrogens that can become anti-periplanar to be removed. Because if a hydrogen cannot become anti-periplanar, I don't care whether the base is small or large, it ain't deprotonating that hydrogen. It has to be anti-periplanar. So in terms of our steps, locate the beta hydrogen, which ones can be removed because they can become anti-periplanar, and then if I'm using a small base, the major product will be the one that's most substituted. And so notice there would be a difference if I gave you a molecule and said, let's do this by E1 or let's do this by E2, because E1, you don't have to take that step. You don't have to say, oh, that beta hydrogen has to be anti-periplanar, because when you form the carbocation, it can always become anti-periplanar. So we have to look at it that way. So what's driving this small base reaction is the formation of the alkene, which one's more stable. So in other words, you're going to get the E1 product, right? If that beta hydrogen can be anti-periplanar. And that is a distinction that we have to keep aware of. Right? Does that make sense? So then we can say, okay, well, in organic chemistry, there's always the yin and the yang. The only real yin and yang we know about now is primaries can't undergo SN1, but they can undergo SN2. Tertiaries can't undergo SN2, but they can undergo SN1. There's going to be yins and yangs about major products, because organic chemistry only becomes successful when, if I can make two different products, I can select the one I want. And it's not just, oh, I select this one, but I can't select that one. No, it's going to be, I can select this one when I want it, I can select this one when I want it. So this is the first, I guess, example of where we have that. So I want to choose the other product. I actually want to deprotonate. Well, let's see. So in other words, with the small base, finish this up. The small base here removes the tertiary. Why? Because when I remove the tertiary hydrogen, I get the most stable double bond. I want to select the primary. What do? Well, I say, you know what? I need a sterically hindered base, because I want that base to be so sterically hindered that it can't get to the tertiary. It can only get to the primary. And so that's easy enough to do. We say, okay, I'm going to take a tertiary butyl alcohol, and I'm going to make the alkoxide the strong base out of that. And typically the counterion for that is potassium. So this is potassium tertiary butoxide. Up here, this was ethoxide, and this is called methoxide. So now if I make a sterically hindered base, and this is just one of many, There's some other ones that in the video I talk about that are my personal favorites, but this will work. It's not modern. And modern ones would have really bizarre structures. But it's the same basic principle. If I want to differentiate between something that's sterically hindered and something that's not, make the thing I'm reacting it with very sterically hindered, and it'll go to the one that's not. So in this case, the tertiary butoxide, now what happens with the energy diagram is there's a huge difference in transition state energy. Because trying to jam this tertiary butoxide over here to deprotonate that hydrogen, it's sterically hindered, the hydrogen's got steric hindrance around it, the transition state energy shoots up. It's going to be less so with the tertiary butoxide. So in this case, what happens is that the tertiary butoxide chooses its product based on the difference in transition state energy, not the final product energy. So in this case, the tertiary butoxide would actually deprotonate the primary system, the primary hydrogen first, and only. So that now I can select my major product based on steric hindrance. So the last thing, so if I go back to this slide, notice that A would have been the product if I used tertiary butoxide as my base, and B, the most substituted product, would have been my base if I used NH2 minus, or I guess the book really likes ethoxide. So if I used either of those two bases, B would be my major product. If I use tertiary butoxide, I get A. So now I have the ability to pick which double bond I want to form. Now what we need to do is we need to apply this to cyclohexane rings, which is what we'll do on Monday, as well as hit the highlights in Chapter 11. So I just released Chapter 11 before class, so that if you read through Chapter 11, hopefully it's kind of review. But we'll finish up Chapter 10. Any questions? On Monday, we'll wrap up SN1, SN2, E1, and E2. Okay? And your practice problems graded practice problems will be due. If you have any questions, again, email me, put them up on Piazza.